This is how AI optimizes my schedule. This meeting
This
got
is
canceled.
how AI
Hooray,
optimizes
we didn't
my
really
schedule.
want to go
This
anyway.
meeting
This
got
is how
canceled.
AI
Hooray,
optimizes
we
my
didn't really
schedule.
want to go
This
anyway.
meeting got
This is how
canceled.
AI
optimizes
optimizes
my
my
schedule.
schedule.
You can't escape thermal fluctuations. They just inevitably can't escape thermal fluctuations. They just inevitably drop it to zero thermal fluctuations. They just inevitably drop it to zero thermal fluctuations. They just inevitably drop it to zero thermal fluctuations. They just inevitably drop it to zero thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of thermal fluctuations. They just inevitably drop it like the beginning of ther
What if the next big technology was actually a really What if the next big technology was actually the processors in your computer? The next big technology was actually processors in your computer. The next big technology was actually the processors in your computer. The next big They think in ones and zeros. But this processor thinks in waves. This is an analog processor, and it might allow us to totally rethink computing from the ground up.
Oh, wow. Can cut through anything.
For the last few decades, digital computing has always been driven by software, and it became very easy to use and very easy to build applications. But all of the information in the world is natively analog. And so what analog processing allows us to do is understand and potentially inference and gather insights from that data in its rawest form.
But just like the digital processors you know, it can still be programmed with software. And that's kind of a big deal.
Imagine being able to build new devices that use AI and machine learning algorithms, but yet use 1,000th of the energy that they use from a digital perspective. And so you get all those benefits of analog, the power, the efficiency, the accuracy, but now you can use a software to program it very quickly.
Does all processing need to be digital? How will analog processors change the way our computers work and interact with us? This is Hard Reset, a series about rebuilding our world from scratch.
Hey everyone, real quick, we're trying something new at Hard Reset. This is a quick message about our sponsor for this episode, BetterHelp. Now, I want to make sure you know Hard Reset will never take sponsorship money from our subjects, like Aspinity, which is the company we're profiling in this episode. But sponsorships from other companies like BetterHelp will make it easier for us to tell more stories we know you will love. And BetterHelp is a company we're happy to talk about. Frankly, at Hard Reset, one of the main things we're always asking ourselves as we develop stories is, what are the assumptions about the way the world works that we should rethink? And personally, I think we need to rethink our...
In my 40 years on Earth, I've seen almost everything go digital. I remember watching Terminator 2 on VHS in the
How do I clean an aioli stain?
Use Tide.
Do crabs have eyebrows?
If it's got to be clean, it's got to be Tide.
Hi, my name is Miran Domanko from the company RLS, and I'm the product manager for Exim Rotary Absolute Encoders. Whether you're building a...
In my 40 years on Earth, I've seen almost everything go digital. I remember watching Terminator 2 on VHS in the 90s. That was analog. The 4K screen you're watching this YouTube video on today, that's digital. It's the same with vinyl records and cassette Walkman, both analog, and now digital smartphones and MP3s. Most of our world has completely gone digital. So when I heard that there may be an analog computing revolution in the making, I was pretty confused and skeptical. Digital is so vastly superior, it just didn't make any sense. So I started digging, and I was blown away with what I discovered. It's a tale of compute power, efficiency, AI, neural networks, betrayal and revenge. Okay, maybe not the betrayal and revenge, but this story is pretty amazing. So let's figure this out together. I'm Ricky, and this is 2-Bit Da Vinci. This video is brought to you by Roborock. Let's start with what these terms actually mean. Analog, or analog, as it's been shortened, just means having agreement or relation with something else, like an analogy in storytelling. Take, for example, old film cameras. These were analog because they were an analog representation of the real world. In fact, early cameras were nothing more than a box with a circular cutout allowing light in and leaving an etched image that was analogous to the real world. Maybe a bit blurry and fuzzy, black and white, or upside down, but analogous nonetheless. The most famous analog devices that we romanticize about today are vinyl record players. This analog device stores sound analogously in grooves on a vinyl record. Many love the rich character of records for this reason, because any attempt to digitize sound comes with a trade-off. Imagine this sound wave, which can pretty much be represented as grooves on vinyl as it is, but a digital recording has to convert this into ones and zeros. Early digital recordings were low quality, as low as 8-bit, or a string of 8 ones and zeros with a maximum combination of 256 values. CDs are 16-bit with 65,536 possible values. The sample rate is how many samples are recorded per second. 44 kilohertz is common, and a high-quality audio recording can be 96 kilohertz. So with a higher sampling rate and higher bit depth, you can see that the digital approximation of the analog sound wave gets closer and closer. It's why today's high-quality digital music on platforms like Spotify or Apple Music sound so much better, but some still prefer good old vinyl. Sound off in the comments below where do you come down on the great audio debate, digital or vinyl. And this is a great example of how digital computers work. Everything is a series of ones and zeros, and grouped together, it can make some beautiful music. Sure, digital is an approximation, but it's very precise. In fact, if you download the same song twice, you're gonna get identical carbon copies, whereas vinyl records are all gonna be a little bit different. Close, of course, but no two will be exactly the same. Digital computers are general purpose. This MacBook can play solitaire or run Blender or Final Cut Pro. Generally, analog computers are much more bespoke, single use case devices, made to just do one thing. Digital computers are exact and precise with high repeatability. Analog computers use voltages, resistors, and hardware that will all vary slightly, leading to close but not exactly accurate or repeatable results. But analog computers do have some benefits, otherwise we probably wouldn't be making this video, right? Analog computers are actually quite powerful for a specific task, very fast, and very energy efficient. And I think I'm starting to see where this is headed. I made a video recently on how the internet and all the data centers in the world consume roughly 1% of all the world's electricity. And with the rise of AI and neural network training, that's about to explode. And if you're thinking AI probably has something to do with this, you'd be correct. Artificial neural networks are one of the hottest things in tech right now. They're actually nothing new, but they've matured to such a level recently as to be pretty damn mind-blowing. AI is slowly making so many things possible, from better recommendations on Netflix to detecting burglars on your camera doorbell. But my favorite use case has to be smart machines like our sponsor this week, Roborock, and this, the S8 Pro Ultra. You guys know I value my time above all. I don't go grocery shopping, I have it delivered. And now I don't even vacuum or mop my floors. The S8 Pro Ultra has 6,000 pascals of suction power. That's more powerful than my regular vacuum. One of the biggest advancements thanks to AI is the reactive 3D obstacle avoidance, which identifies lots of common household items and avoids them. Its dual roller riser brush does a remarkable job of picking up everything from dust and pet hair to food waste and cereal. And of course, with its amazing robo dock, it automatically empties the dustbin so you never have to bother. But the amazing part is it'll even mop your floors. With its VibraRinse 2.0 mopping tech, it'll vibrate up to 3,000 times per minute for amazing mopping performance. When it encounters a rug or carpet, it can lift the mopping head and keep vacuuming automatically. I cannot tell you how much I love the S8 Pro Ultra. Let it get to work keeping your house clean so you can get back to doing the things you love. Use our links in the description to check out the Roborock S8 Pro Ultra and win back your time today. Huge thanks to Roborock and you for supporting the show. Let's do a quick rundown of what a neural network is. Artificial just means that the architecture and underpinnings are designed around the idea of the neurons in our brain. Our brain has over 86 billion neurons that connect through synapses. Analogously, in an artificial neural network, the nodes are interconnected to other nodes to form a network. Keeping things pretty high level, you can think of a neural network as a series of layers, read from left to right. The first column is the input layer. This can be as simple as one input for simplicity or hundreds or thousands. Imagine each input corresponding to the pixel of an image for a self-driving computer, for example. The next columns are hidden layers. If you've ever heard the term deep neural network, that just means a lot of hidden layers where a lot of manipulation is happening. Finally, you have the output layer, where the nodes finally give answers. The magic happens when you break down the operations at play. Ultimately, it's matrix multiplication. So we can assign a value to each input. How many inputs you need is a function of what you're trying to do. But I think the easiest way to visualize this is an image recognition AI, for example. What's so genius about neural networks is how you train them. If you want a neural network to identify shapes, for example, you start with a training set of circles and triangles and squares. The key is that the weight value you assign to each node. The value for the next node is equal to each input node times the weight, plus the node times the weight of every other node. This is the matrix multiplication operation. You start with a random series of numbers for the weight, and wait for an incorrect answer, like the model claiming a square is a circle. When this happens, you assign the values to the weight, influencing the future output. Do this over and over again with more and more data, and models start getting better and better at predicting what actually is a rectangle and what's a circle. As you can imagine, the number of inputs can get really insane, and so can the number of internal hidden layers. Much like the sampling rate or bit depth for higher quality audio recordings, this is how you get more robust neural networks. but it all comes at the cost of a really high level of compute power. I've given really broad strokes here, but if you want a deeper dive on neural networks or if you're curious about more, sound off in the comments below and we can make future episodes. For digital computers, the fastest means of storing data is memory via the memory bus. So larger complex neural networks can have massive amounts of data, particularly the weight we discussed in memory. This has some challenges, but how does an analog computer perform the same task? Let's think about solar panels, something I think about a lot. Connect two solar panels in parallel and the current adds up. So addition is as simple as combining different currents, which is something analog computers are very good at. But remember that weight value? That's multiplied to each node before adding them up. So how could an analog computer perform multiplication? Well, keeping our electrical engineering hats on, the easiest way would be adding resistance. Ohm's law tells us that voltage equals IR, or you can reorganize it in a different way and think of it as current equals voltage divided by resistance. So if we set the node's value
Villa is a curated luxury experience. All my staff has to do is execute my wishes. It's good to actually take the whole thing down.
To current and pick a resistor to match the weight value, we could measure the current and figure out the multiplied value. Doing math with an analog computer. It's pretty amazing, right? But we have some problems. It wouldn't be practical to change thousands of resistors, right? Imagine if you wanted to update your neural network with new weight data that you just trained. You'd have to change out thousands of resistors, and that's not practical. And this is why digital computers are so amazing. As you can imagine, AI companies are constantly training their models and getting better and better data prediction. So it's critical that these machines can be updated more easily. So to solve this problem, analog chip startup Mythic has some pretty clever solutions. I just came across a video from Veritasium, one of my favorite YouTube channels, that did an on-site with Mythic. I'll put a link in the description. But the key is how data or variables like weight values is stored. In a digital computer, it's stored in memory. Each weight value can be stored in arrays or arrays of arrays. And when the calculation is needed, the digital CPU pulls up that value in memory. The problem with memory, though, is that it needs to be powered up to retain the value. Think about your smartphone versus an e-ink reader screen. The smartphone needs power constantly to keep powered on. If the battery dies, your screen goes black. But with e-ink, electricity is used to permanently store values on the screen. And even if the device dies, it'll keep showing the last created image. And that's the key. So how does Mythic solve this? Now this is pure genius from an engineering perspective. They use the same SSD flash drives that you have in your SD cards or hard drives like in this MacBook, except they use it in an entirely different way. Hard drives are digital devices, so each storage cell usually holds either a 1 or a 0 that makes up a larger data packet. Typically in flash storage, a positive voltage is applied to the control gate, which attracts electrons through an isolating barrier into the floating gate. Unlike memory, this is permanent. So when the voltage is removed, these electrons stay in the floating gate. This prevents current from flowing and registers as a 0 on the digital domain. This is why your data on your laptop or smartphone persists even if you power it off or the battery dies. What's genius about Mythic's approach is that instead of treating this as a switch, either on or off, 1 or 0, they apply only a certain amount of voltage to only move a certain number of electrons. The higher the number of electrons, the higher the resistance, kind of like the physical resistors in our analog computers earlier. But now you can change its value by resetting and applying a different number of electrons by changing the values on the gates. Back to Ohm's law, the current I is equal to V divided by R, which is a division operation, but it's the same as V times 1 divided by R, 1 over R. So essentially, by setting the resistance of the gate and measuring the current, we'd get the desired multiplication operation. Add the values from nodes with different current values, times resistance, the weight value, and you just did neural network math using an analog computer. And this is seriously genius because now you can write all the model's weight data physically into flash storage. Then you don't need a power RAM or anything else, just measure the voltage in an analog way get the resistance, and get your weight data. And in this way, an analog computer can do matrix multiplication almost as well as a digital computer with a fraction of the energy required. Mythic claims their analog CPUs can do the same workload as a 100-watt digital CPU with as little as 3 watts of power. Now, it's not all good news though, because remember, the analog computers aren't as accurate as digital. The 0 or 1 in a digital flash gate makes up a larger block of data, often with a checksum to ensure the value of 0.7654 is exactly 0.7654 each and every time. With the resistance approach and storing electrons in flash gates, it's not going to always be as precise. But for the purposes of making an accurate identification for a visual model, for example, 90-95% accuracy might be just fine. One more challenge worth noting is runaway errors. Like I mentioned, the current value will be close but not exact, and so will the resistance value. Just one calculation isn't such a big deal, but add these up and you can have a runaway effect. Imagine trying to measure your room by measuring a plank of your hardwood floor. You have 100 planks and each measures to be 1 foot or 1 meter for our non-Americans out there. You might be tempted to think, for saving time, that if you have 100 planks and each plank is a foot, you'd have a 100-foot room. But each plank can be off by about 5%. So that means after 10 planks, you can be off by about half a foot or half a meter. And by 100 planks, you can be off by as much as 5 feet or 5 meters. Now that's compounding runaway errors, and it's a problem with the more calculations being performed. Mythic solves this by converting from analog to digital along the way, which adds complexity and consumes more power, but it's a necessary evil. The bottom line is this: analog computers are really fast, efficient, and low power consumption, but they're not as accurate, and they aren't going to replace digital computers. Instead, think about this: a small bit of plastic made out of a very complex form. The forms are made of very high tolerance, high strength steel. That way you can stamp out this part time and time again for years. But the end product is this simple part that costs pennies. Analog computers won't cost pennies, especially early on. But when they reach economies of scale, it's likely they will be much cheaper and abundant than digital processors. The steel in this analogy would be the super high-end GPU-based supercomputer that runs on digital and handles all the training data and a slew of other programs. But from that training, we could load this data onto analog computers to actually run the simulations and models. Here are just a few potential use cases. Imagine an AI model running on a cheap, low-power analog computer that runs a camera and detects the presence of children. You can mount this all around your pool and power it with a small solar cell, like from a solar walkway light. And it could run all day and send an alert to your smartphone if your children ever get too close to the pool. Being wireless, it wouldn't need to send all this data out to get processed. It could do it all on site, on the chip, and it only has to send a notification if children are detected. Or imagine AI image detection sensors placed all around assembly lines looking for misalignment or other problems. We did a video on the future of farming and those robots that are looking at weeds and shooting lasers to kill weeds. Imagine if all of that could be done on analog computers. As the scale for our hunger for these sensors increase, energy consumption starts to play a bigger role, not to mention cost. So yeah, not replacing digital computers, but by being the backbone that neural networks are run on, we might just be looking at the beginning of an analog computing renaissance. So what do you think? Are analog computers going to be a big part of the fabric of the future? If you want to see more videos about any of these topics I've talked about here, don't be shy, sound off in the comments below. And while you're down there, hit the like button and subscribe. All right, I'm Rick Tuba Da Vinci. Thank you so much for watching. Until next week, check out this video next.
Are you tired of your hair breaking after waiting years for it to grow? New Pantene Infinite Lengths with biotin and collagen repairs every inch as well as a leading $60 luxury brand. Up to 90% less breakage. If you know it's Pantene.
Hey guys, welcome to this session by IntelliPat. In this session, we are going to completely learn about JavaScript. So JavaScript is a language which can be used to create dynamic web pages and also can be used for backend programming. So when it comes to web development, JavaScript is the complete package. So now, before moving on to this session, please subscribe to our channel so that you don't miss our upcoming videos, and also leave a like if you enjoy our content. Before moving on with the session, let's take a quick glance at the agenda. We'll start off with what is JavaScript and why do we need it. Once that is done, we'll understand what can we build using JavaScript. After that, we'll understand the basic concepts in JavaScript and also the ES6 features of JavaScript. Once that is done, we'll move on to document object model and JavaScript events. After that, we'll move on to asynchronous JavaScript and we'll learn more about it. Once all that is done, we'll basically learn about a popular JavaScript framework called Node.js. So now, once all the concepts are done, we'll start the practical bit.
Eric Hainer is a Canadian computer scientist who developed an interesting unified approach to logic and arithmetic. It's quite remarkable. He introduces many cool ideas, some of them perhaps far-fetched, but what I like most about them is that they make you think, and they give you new insights. They are the perfect example of what we're trying to do on this channel, looking at familiar things from a new angle. Some time ago, I asked you if you would be interested in a video about Hainer's new system, and many of you responded positively. So, here we go. Logic begins with two opposite values that are often called true and false, but you can also think of them as on and off, or high and low, or good and bad, or any other pair of values that are opposites of each other. Hainer calls them top and bottom, and gives them these two symbols. The names top and bottom come from a theory about partially ordered sets, where the top element is larger than all others, and the bottom element is smaller than all others. Hainer is very sensitive to the visual shape of mathematical symbols. When symbols are carefully chosen, they sharpen your intuition and make your calculations easier. So it's no coincidence that the top and bottom symbols are each other's vertical duals. This choice reflects the fact that they are also mathematically opposite to each other. The two binary values can be combined using various operators. The first one is typically called AND, because its value is true only when both of its inputs are true. But Hainer looks at this differently. He urges us to think of top and bottom as two values that are ordered. Top is the largest of all possible values, and bottom the smallest. This allows us to interpret the AND operation as the minimum instead. Its value is top only when both inputs are top. As soon as one of the inputs is bottom, it pulls the minimum down, and then the other input value becomes irrelevant. Another classical operation is called OR. Its value is true when one input or the other is true, or possibly both. In our new interpretation, this is the maximum of the two input values. As soon as one of them is top, it pulls up the maximum and the result is also top. The classical symbols for AND and OR are these wedges, pointing in opposite directions. Again, this is a perfect choice because the operations are dual to each other. But they are also perfect in another respect. They are symmetric around a vertical axis. This helps you remember that these operations are commutative. X and Y has the same value as Y and X. The maximum of A and B is the same as the maximum of B and A, and so on. Hainer carefully chooses his symbols so that they reflect these algebraic properties. He sometimes uses these arrows instead of the wedges, because they spell minimum and maximum more clearly. And they are still vertically symmetric and horizontally dual. Here's another key operation on binary values. It's called implication, and it says that if the first input is true, then the second must be true as well. If the first input is false, the second input can be whatever you want. This is one of those things in logic that confuses the hell out of students. How on earth can something false imply something true? It would be like saying, if 2 plus 2 equals 5, then I am the Emperor of China. Logically, this is absolutely true. Intuitively, it makes no sense. But if you look at it from an ordering perspective, it all becomes clear. Think of implication as less than or equal to. Because bottom is less than top, this rule now makes perfect sense. So this idea of using order theory as a model for binary logic isn't as weird as it may seem at first. It's actually very insightful. Think about numbers and proofs for a moment. If x is less than 4, then it's also less than 6. The first condition implies the second, and this is how you would typically use implication in mathematical proofs. But now look at it like this. The condition that x is less than 4 is stricter than the condition that x is less than 6. Fewer values for x satisfy it. And so you could say that the first condition is less true than the second one. Mathematical statements are ordered from bottom to top, from the falsest statements that aren't satisfied by anything, to the truest ones that are satisfied by everything. So even the notion of mathematical proofs can be reformulated in terms of ordering. Even though top and bottom are dual to each other, mathematicians have a preference for top. When a logic expression evaluates to top or true, we say that it's a theorem, and we award it special status among all other mathematical statements. Some statements are always true. They evaluate to top no matter what values you fill in for the variables. Those statements are called laws. A good example is the law of the excluded middle. No matter what value you give to the binary variable q, the value of q or not q, a good example is the law of the excluded middle. No matter what value you give to the binary variable q, the value of q or not q is always true. You can easily prove this yourself by just looking at the truth tables. The next thing we're gonna do is extend binary logic to arithmetic. In computer science, you will often see the number 0 used for false and 1 for true. Heiner's solution is much more surprising, until you remember that it's based on ordering. Top is larger than all possible values, including numeric values, so it makes a lot of sense to model it as plus infinity. Likewise, bottom becomes minus infinity. This way, binary logic is embedded inside the number system in a very natural way. This turns out to be a genius move, because it gives us countless cool connections between logic and numbers. Here's one of my favorite examples. Start with two positive numbers a and b. Take their maximum. Then change its sign so that it flips over to the other side of the number line. So we have the inverse of the maximum. Now flip the original two numbers so that they both become negative. Take the minimum. I'm sure it's no surprise that this gives us the same result as before. We can write this down as a law. The inverse of the maximum is always going to be the minimum of the inverses. I don't know how familiar you are with binary logic. You may have seen this law before. Let me replace Heiner's minimum and maximum symbols with the more traditional wedge symbols. Does this ring any bells? It's the well-known law of De Morgan. Is it currently raining and snowing? If not, then it must be either not raining or not snowing, or possibly neither. The cool thing is that the same law now works for binary truth values and for numbers. I think that's absolutely brilliant. There are many more examples, such as the inverse of the inverse is the original. See if you can put these other laws into words, both for binary logic and for numeric values of x. You can share your interpretation in the comments, so that we can discuss how these connections between logic and arithmetic can be understood. Now, we have to be careful, because there are laws from binary logic that don't carry over to arithmetic. One important example is the law of the excluded middle. When q can only be a binary value, q or not q is always true. But when q is a number, this formula asks us to calculate the maximum of q and negative q. The result is the absolute value of q, which is definitely not equal to true or top or plus infinity. So the law of the excluded middle is no longer a law in our extended system. This is okay. It's actually very common. Whenever you extend a system with new elements and new possibilities, you sometimes also lose things. We saw this before when extending the reals to the complex numbers, the quaternions and the octonions. We lost things like commutativity and even associativity. You can't always get things for free. A function maps elements from one set to another in a certain way. When you define a new function, you place the input variable between parentheses, and then you use that variable inside the expression on the right. You can use any name you want for this input variable. It exists only inside the function. You can't use it on the outside. Hehner's notation makes this more explicit by enclosing the function definition in angle brackets. The variable exists only inside the brackets. In computer science, this is called a scope. Variables exist only inside their scope. They are local to their scope. You may think that this new notation is overkill, but note that it contains more information than the original definition. It tells you the domain of the input variable. It tells you that x is a natural number, not something else. The biggest advantage of the new notation is that it also works for many other mathematical symbols that introduce new local variables. Think about the sigma notation for sums. This example introduces a new variable I that takes on all the values from 1 to 10 and then sums up the squares of those values. Hehner simply puts a plus operator in front of the angle brackets. You could even make the plus symbol slightly bigger to stress that it operates on lots of values in sequence. The advantage is that you don't have to invent a new symbol, such as the sigma. You can just use any existing binary operator. Here's how you would write a product. Just use the binary multiplication symbol. We still specify the range of input values, but now we do so consistently inside the brackets, where the scope of the variable is clearly delineated. You can also take the minimum or the maximum over a collection of numeric values. If the output expression of the function is binary, true or false, the minimum and maximum become the logical and or operators. And if you think about this a little longer, you might realize that this plays the role of the traditional for all and exists operators. For all x means that you're going to evaluate the output expression for each value of x, and then check whether all of those output values are true. This means that you implicitly put a binary AND operator between all of those output values. The new notation makes this more visible by placing a big AND operator right at the start. So once again, we didn't have to invent a new symbol like the upside down letter A. I remember being charmed when I saw this for the first time. There really is no difference between the minimum, the logical AND, and the for all quantifier. They all do the same thing, so they should all be written with the same symbol. This makes it much easier to understand what the exists quantifier does. It just puts an implicit OR between all the expressions. As soon as one of them is true, the entire thing becomes true. Let's look at that simple function definition again. The original has a name. It's called f. The new definition doesn't have a name. It's just a thing that maps inputs to outputs. If you want to give it a name, you can. Just assign the thing to a brand new variable, like you always do. And since, by definition, the bracket expression on the right is now the same thing as the letter f on the left, we can now write a big sum like this. You no longer see the range of input variables because it's carried around inside the letter f, if you will. This allows for some very compact notation. Here are the laws of de Morgan again. Look at how brief they are. Hainer even suggests that we could drop the f entirely, which reveals that de Morgan basically says that AND is the opposite of OR. Personally, I would say that this is pushing the limits of readability. You don't want your notation to become so compact that you forget what it means. But for lengthy calculations, this might be a huge time saver. A set is a bunch of elements that you put together inside a box. The set itself is the box, and the elements of the set are the contents of the box. Traditionally, you write a set of elements like this. You can think of the curly braces as the box. But Hainer goes one step further, and once again this is a really curious and fruitful way of looking at things. These commas are not just punctuation signs that separate the elements from each other. The comma is a binary operator. It takes two inputs, let's say the numbers 2 and 3. It combines them into a bunch. A bunch is just a collection of objects that are not yet placed inside a container. The curly braces are a unary operator that turns a bunch into a set. It puts the bunch of elements into a box. The empty set is just a box with no elements inside. An empty bunch is literally nothing, not even a box. Seeing the comma and the braces as operators rather than mere punctuation marks is extremely clever. You probably know that the order of the elements in a set is irrelevant. For Hainer, this can only mean one thing. The comma operator is commutative. It's so elegant to reuse the concept of commutativity here in a totally different context. And it gets even better. The comma operator is also idempotent. This simply means that if you add the same element into a bunch or set twice, you get only a single copy of it. This is similar to how projections are idempotent because projecting twice is the same as projecting only once. So we turn the comma into a full-blown operator with properties that it shares with many other operators. This efficiency of concepts is very typical of Hainer's system, and it's the main reason I like it so much. In set theory, you can specify that something is inside a set by using the element_of operator. Hainer prefers to write this with a colon. This expression says that n is a natural number. One important difference is that NOT is the bunch of all natural numbers. It's not a set. We should use bunches rather than sets, especially when specifying the domain for a variable. That's because there's one final trick we can pull. You've heard about distributivity, right? Multiplication distributes over addition, so you end up repeating the factor of 2 for each of the terms. Well then, since the comma is now a binary operator, it can participate in distributivity. All other operators distribute over the comma operator. So when you say not plus 7, you get the bunch of all natural numbers that are at least 7. And 2 times int is the bunch of even integers. Not squared gives you all the square numbers, and so on. The reason this works so well is because we are operating directly on bunches, so we don't have to unpack and repack anything, which makes the formulas extremely elegant. It's now easy to construct new bunches from other bunches, and once again, you just keep using the same old operators that we already had. This is especially powerful in computer science, where you have to be very precise about the domain of each variable. You can now easily start playing around with these ideas yourself. If the curly braces turn a bunch into a set, there could also be an inverse operator that turns the set back into a bunch. It takes the elements out of the set and throws away the box. Let us know in the comments what other kinds of clever tricks you can come up with. There are a few links in the description to Heiner's PDFs that you can download if you like this kind of out-of-the-box thinking. Don't forget to subscribe and like the video. And if you want more content like this, consider supporting us on Patreon. Our channel needs your financial support, so thank you.
Smooth Melting Lindor by the Lind Maitre Chocolatier.
The user experience of the internet is broken. It doesn't have to be that way. Solana is really the foundation of a new internet. I think that we are going to be a part of the solution to that. Within Drip itself, you are subscribing to creators that you like, and in return, they're giving you their best work that you can own. When you like a piece of content on Drip, you're actually giving them a single droplet. When you add that up across tens of thousands of fans, it becomes real income from that. It becomes meaningful. Compression basically allowed Drip to exist. I mean, without Solana compression, Drip isn't possible. And honestly, we would lose the heart of the product, which is its accessibility.
Hi, my name is Alina, and I would like to give you a few reasons why you should consider dating a young Slavic lady. You can choose a potential spouse from Ukraine, Russia, Belarus. Geography is boundless. Have you noticed that Slavic women have become more and more popular? I mean that they are everywhere. In famous magazines, on Instagram as top bloggers, on the runways and on the billboards. More importantly, they are in men's hearts, because most of them have everything that an object of fascination is supposed to have. Natural beauty, stunning bodies, charisma and light temper. Yes, these ladies are beautiful, and even you can't deny that a lot of men are physically attracted to them. Anyway, Slavic women are truly respect and appreciate American men. These ladies are passionate. They have been raised to respect family and traditional values. American guys are usually less passionate and emotional than Slavic men. It may seem that this could stop the local girls from looking for a foreign husband, but opposites attract. They like men from American countries because they are more ambitious, financially and socially responsible, and after all, they are just more rational. Lots of girls are dreaming of a good husband from America. So, what's the problem? Choose a dating site, a few weeks of conversation, personal meetings, and voila! A new happy couple is here. And of course, Slavic women speak English fluently. It's important, right? Yes, there are lots of translation tools to make convo between foreign people clear, but it's always easier and more pleasant to make a nice conversation with a girl without translators' help. Have you ever noticed how the members of Slavic families treat each other? This is what a man gets when they marry a Slavic. Family and motherhood are sacred to most girls from Slavic countries. Women bring harmony to men's lives, special traditions where their husband can feel at home and enjoy a safe harbor. Slavic women do not pay much attention to the age difference. They do believe that a good personality stands first. More of it, they likely prefer men over 40, because they are more wise and stable. Sounds perfect, right? So why wait? Dare and take what is yours. Click the link below and take a 2-minute compatibility test with the young Slavic ladies.
Now, this book is called Understanding Deep Learning to distinguish it from other more practical books which focus on things like coding. This book is all about the ideas which underlie deep learning. After reading this book, you will be able to apply deep learning to novel situations where there is no existing recipe for success.
The book starts straight away by describing deep neural networks, and it takes you through the training, testing pipeline, how do we improve their performance, Then it starts talking about different architectures, convolutional networks, residual networks, graph neural networks, transformers. There's a long section on generative models, normalizing flows, VAEs, GANs, diffusion models, a short section on reinforcement learning. At the end, there are two chapters that I think are really interesting. There's a chapter called Why Do Deep Neural Networks Work, where I try and interrogate a bit why we need this particular kind of architecture, why it's easy to train, why it generalizes. We don't really have answers to those things, but I present some of the evidence there is. And the final chapter is a chapter on ethics. I think the book will be useful if you know nothing about deep learning at all. It will take you from scratch to somewhere close-ish to the cutting edge. If you're teaching deep learning, it'll be an incredibly useful resource. It has 275 figures, most of which are new and represent things in different ways. It also has a whole bunch of Python notebooks. If you're part of the rank and file of machine learning practitioners or researchers, it'll fill in the gaps in your knowledge and maybe make you think about things in a different way. I think even my initial description of deep neural networks is a bit different to how they're usually described. And I think you'll learn a lot from it because I am a member of the rank and file of deep learning practitioners, and I learned a lot about something too. If your name is Jeff Hinton or Jürgen Schmidt-Huber, I can see it might not be that useful to you.
Well, you never know.
You never know.
So the title is a little bit ironic because at the time of writing, nobody understands how deep learning models work. Literally nobody. Now, deep learning models, they learn piecewise linear functions. And as you'll know from our episode on the spline theory of deep learning, they chop up the input space into many, many little regions. In fact, most models have more regions than there are atoms in the universe. And frankly, it's a mystery. It's a goddamn mystery. How do these models generalize? And how do they learn these functions? Nobody knows. So why does deep learning work? It's remarkable that the fitting algorithm doesn't get trapped in local minima or stuck near saddle points, and that it can efficiently recruit spare model capacity to fit unexplained training data wherever they lie. Perhaps this success is less surprising when there are far more parameters than training data. However, it's debatable whether this is generally the case. AlexNet had 60 million parameters and was trained with 1 million data points. However, to complicate matters, each training example was augmented with 2048 transformations. GPT-3 had 175 billion parameters and was trained on 300 billion tokens. There's not a clear-cut case that either model was over-parameterized, and yet they were successfully trained. In short, it's surprising that we can fit deep networks reliably and efficiently. Either the data, the models, the training algorithms, or some combination of all three must have special properties which make this possible. The efficient fitting of deep learning models is startling, and their generalization is dumbfounding. First, it's not obvious a priori that typical datasets are sufficient to characterize the input-output mapping. Second, deep networks describe very complicated functions. And third, generalization gets better with more parameters. This surfeit of parameters gives the model latitude to do almost anything between the training data, and yet it behaves sensibly. It's neither obvious that we should be able to fit deep networks, nor that they should generalize. A priori, deep learning should not work, and yet it does. The success of deep learning is surprising. In his book, Professor Prince discussed the challenges of optimizing high-dimensional loss functions and argued that the over-parameterization and choice of activation function are the two most important factors that make this tractable in deep networks. He showed that, during training, the parameters move through a low-dimensional subspace to a family of connected global minima, and that local minima are not apparent. So as we over-parameterize these models, generalization increases, but it's also related to other things like the flatness of the minimum and inductive priors. It appears that both a large number of parameters and multiple network layers are required for good generalization, although we do not yet know why. Many questions remain unanswered. We do not currently have any prescriptive theory that will allow us to predict the circumstances in which training and generalization will succeed or fail. We do not know the limits of learning in deep networks or whether much more efficient models are possible. We do not know whether there are parameters that would generalize better within the same model. The study of deep learning is often driven by empirical demonstrations, and Simon concedes that these are undeniably impressive, but they are not yet matched by our understanding of deep learning mechanisms. On ethics, Simon said that it would be irresponsible to write this book without discussing the ethical implications of artificial intelligence. This potent technology will change the world in ways arguably not too dissimilar to electricity or the internal combustion engine, the transistor, or the internet. The potential benefits in healthcare, design, entertainment, transport, education, and almost every area of commerce are enormous. However, scientists and engineers are often unrealistically optimistic about the outcomes of their work, and the potential for harm is just as great. Simon argues that everyone studying or researching or even writing books about artificial intelligence should contemplate to what degree scientists are accountable for the uses of their technology. He said that we should consider that capitalism primarily drives the development of AI and that legal advances and deployment for social good are likely to lag significantly behind. We should reflect on whether it's possible, as scientists and engineers, to control progress in this field and to reduce the potential for harm. We should consider what kind of organizations we are prepared to work for. How serious are they in their commitment to reducing the potential harms of AI? Are they simply ethics washing to reduce reputational risk? Or do they actually implement mechanisms to halt ethically suspect projects? Simon invites readers of his book to investigate these issues further. It's undeniable that artificial intelligence will radically change society for better or worse. However, optimistic visions of a future utopian society driven by AI should be met with caution and a healthy dose of critical reflection. Many of the touted benefits of AI are beneficial only in certain contexts and only to a subset of society. Now, the book cites Green, 2019, who highlighted that one project developed using AI to enhance police accountability and alternatives to incarceration, and another developed to increase security through predictive policing, are both advertised as AI for social good, in big air quotes. Assigning this label is a value judgment that lacks any grounding principles. One community's good is another's harm. Ethical AI is a collective action problem, and the chapter concludes with an appeal to scientists to consider the moral and ethical implications of their work. Every ethical issue is not within the control of every individual computer scientist. However, this does not imply that researchers have no responsibility whatsoever to consider and mitigate, where they can, the potential misuse of the systems they create. We scuba dive, you know, we actually do stuff. And maybe I'm just being a human chauvinist, but I'm completely on board with it becoming embedded in our cognitive ecosystem. But
also GPT does stuff, not very well, but it does it.
Well, does it though? I don't know. Does it do something? I mean, yeah, like in the way a cat flap does stuff. You know, you can make it do things. It can execute code and so on. But I wouldn't say it has agency.
Hello everyone, it's Tim here from MLST, your go-to channel and podcast for all things machine learning, AI and philosophy. Today I'm reaching out with a special request. As you know,
creating content for MLST takes a considerable amount of time and resources. It's a labour of love that I do purely for the fun and passion of the subject, but to keep bringing you the high quality content that you've come to expect, I need your support. Please consider supporting us on Patreon. Every bit helps, although please only donate what is an insignificant amount of money depending on your situation. If you can't afford it, just let me know and I will give you free access to the Patreon's benefits. No questions asked. Anyway, thank you so much for your time, and I can't wait to welcome you to our Patreon family. Signing off for now. Cheers.
Simon, it's an absolute honour to meet you. Welcome to Machine Learning Street Talk.
I'm very glad to be here.
So tell us about yourself.
Well, I actually started my career in psychology. My PhD is in psychology, and then I've been wandering through various parts of science. I worked in neuroscience for a while. I did some early work in augmented reality. I dabbled in medical imaging. In the noughties, I was faculty at UCL, and I worked on computer vision, and I'm probably best known for a book that I wrote at that time. And in the last decade, I've mainly been working in industry, in finance and computer graphics, and I'm currently a professor at the University of Bath, where I have been working on a new book, Understanding Deep Learning, which is going to be published by MIT Press. Sorry, I should say, which is published, which is...
Well, Simon, we were joking before that on your last book you were Ubered. And you're writing a book about computer vision and probabilistic graphical models and so on, and then that Sutskever guy, we'll come back to him later. Well, it wasn't him actually, it was Krzyzewski, but they're all basically Hinton's guys. They released AlexNet, didn't they? And then that was computer vision completely solved.
Right, so my last book was a really ambitious attempt to basically remold the whole of computer vision as I saw it by formulating what was quite an ad hoc selection of methods in terms of probabilistic graphical models, which wasn't at the time necessarily how everybody thought about it. And in 2010, I went on sabbatical to the University of Toronto, and I worked on this book, probably with Alex Krzyzewski in the next room to me, and sharing an office with Jeff Hinton's postdoc, doggedly worked on this book. I released it in 2012, a few months before AlexNet came out, and the entire field took a right-angle turn, leaving my book in the dust. Although I still think it's quite useful, the geometry and stuff is still definitely all valid, and it has a lot of stuff on Bayesian probability. But this book is less ambitious. It's a more sort of straightforward description of where we are with deep learning. It's supposed to be the spiritual successor to Goodfellow, Bengio and Corville, which was published in 2016, so obviously a lot of stuff has happened since then. It takes a sort of pragmatic middle ground between very theoretical stuff with lots of proofs and very practical stuff with lots of code. There are no proofs, there is no code. It's about the ideas that drive deep learning.
Okay, so Simon, when you started writing this book, what was the main idea that you had in your mind?
Well, I think the history of deep learning is that experimentalists have run far ahead of the theory, and we now have this explosion of papers where there is literally an exponential increase in the number of papers being published. And when I say literally, I mean literally. There is a plot in a paper that came out last year where on semi-log y it is a straight line with 4,000 papers being pushed to archive every month. And presumably there's more than that now. Obviously it can't increase exponentially forever. There's a finite number of humans on the planet. They can't all do machine learning research. So there's a staggering quantity of information out there. If you are a new person coming to machine learning or you want to learn something new, it's almost impossible to find good resources. People are learning things from blogs that are written hastily by people who don't always know what they're talking about. And so it seemed to me a really useful thing I could do for the community, where I could write out everything pretty much important that's happened in the last 10 years connected to deep learning with the same notation, illustrated in a modern way without regard for history. I don't start at the perceptron, I jump right in to deep neural networks in 20 pages into the book, not 160 pages, just to save collectively, the community, a giant amount of time.
Yes, and do you think that deep learning is alchemy?
No, it's not alchemy at all. I think in the future what we'll think of it as is the science of modeling functions and probability distributions in very high dimensions. I mean, I think it'll be recast as that in terms of science.
Yeah.
At the moment, we're more concerned with the way we organize our whole community is about results, so we don't really talk about it that way. But I think in 40 years' time, they'll look back and say, well, in the 2010s, they studied how to build functions and how to model probability distributions in dimensions that are higher than, say, 50.
Yeah, so I was tongue-in-cheek on the alchemy point, but I guess number one, people have made some strange analogies to neuroscience and biology. Even the word neuron actually is quite interesting. So it only appears 4 times in your entire book, and 2 of those occasions you are counselling us not to use the word neuron. So let's start with that.
Yeah, and I should say I will probably accidentally use the neuron during this conversation because it's so embedded in our community, but I think it's a terrible analogy. There's no evidence the brain works in any way that deep neural networks do. If you look at the sort of epiphenomena of the brain, you know, of human computation, we seem to have things like short-term memory, we seem to need to dream to lay down memories, we have a modular brain with special parts for recognizing faces, for navigating through the world and so on. There's no evidence that deep learning has any of that. And likewise, there's no evidence that the brain has any of the epiphenomena of deep learning. So, you know, there's no evidence for double descent or adversarial examples or lottery tickets in the brain as far as I'm aware. And this is sort of okay for our community because we know what we're talking about, but now deep learning is becoming a really important thing in the real world. And so we're trying to communicate this to the general public. And we're talking about neurons and neural networks. And that carries with it a lot of baggage. You know, an interesting experiment that everybody watching this should do is go and talk to somebody at a dinner party who knows nothing very much about AI, who works, you know, a lawyer, someone intelligent who works in a completely different field, and ask them what their understanding of current AI is. And almost certainly the answer you will get is that they have no idea. They might be able to give you a couple of buzzwords, but how does it work? They have no idea. And I really disapprove of the neural metaphor just because it comes with a lot of baggage. That sort of implies perhaps that the network's having thoughts or that it's something like us. And that's deeply misleading to people who are outside our community. And of course, everything we're doing is increasingly affecting those people outside our community. And we want to give them sensible information about what it is that we're working on.
Yeah, so, I mean, again, on the alchemy point, we are now dealing with multiple levels of emergence. And what I mean by that is people understand gradient optimization, they understand parameterized models, they don't understand the emergent phenomena, and they reach for analogies, let's say psychology analogies. You know, they talk about things like theory of mind.
I'm not completely convinced there are emergent phenomena, depending on exactly how you define emergent phenomena. For me, an emergent phenomenon would be something where you gradually ramped up the scale and there was suddenly a phase change where you could see new phenomena, I suppose, for want of a better word, suddenly appear with scale. And I'm not sure we've done those experiments super thoroughly. What you're really saying to me is that the statistics of the data on the internet are surprisingly rich, such that we can, complete sentences or translate from one language to another. All of that is just reflecting the statistics that are on the internet. And it is surprising that when you gather that much data and put it together in a network and reproduce those statistics, we see these phenomena. But I don't see that as a property of the network. I see that as a property of the data that we're putting into the network.
Whether it came from the richness of the statistics or not, I think we are looking for mental reference frames to understand said phenomena. It's just we need a way to understand this stuff, right? And psychology has a theory of mind literature that we can use, and we are almost certainly overloading it and bastardizing it. But are you saying we shouldn't do that?
I have the most reductionist view of this possible. I think of when I see a large language model, I see an enormous equation with trillions of terms in it. And we've set the parameters of those terms so it performs some kind of behavior. And I don't think there's any great meaning to that behavior. It's an equation. There are inputs, you compute, you add things, you multiply things. Occasionally, if it's a transformer, you take an exponential.
Yeah.
And out comes some numbers at the other end that you then translate into words. And I don't think it can be understood on any deeper level than that.
But couldn't you make the argument then that there's nothing special about our mental states or our behavior because we are also at some level just performing simple calculations?
I think you could make that argument, but there's more going on because we have a larger variety of brain systems interacting with each other, some of which have been built on top of each other during evolution. So there's more structure in the actual model. You know, it's not, at the very least, the human brain is not one equation, it's a bunch of equations interacting with each other in a complicated way. So whether that maps to the kind of constructs you're talking about, I don't know, but I see the human brain as being quite a different thing to that.
It's mostly a matter of complexity. So when you have this rich kind of functional dynamics of things interacting in the physical world, you have the emergence of agency and all sorts of moral status and so on. And you're basically just making the statement that in neural networks, we're just nowhere near to that kind of emergence.
I mean, you're asking me questions that nobody knows the answer to. The only existing model we have that works is the human mind, and that seems to work upon quite different principles than just scale.
Yes.
I think something that's very interesting about transformers, though, is I was arguing before that I don't like this neural analogy, but actually the large language models like ChatGPT are the closest thing we have to something like the human brain, because they do, just as I expressed, map an input to an output, but they also have this kind of short-term memory, which is the context window. So in a sense, and it's ironic that we don't refer to that in terms of a neural analogy, because that to me is the first thing we've built that sort of looks something like the human mind. You have this context and it makes the next prediction of the token based on that context, and in principle you could then operate on the previous context. The system itself could operate on the previous context. It could summarize it, it could file things away, it could ask itself to generate other different hypotheses to explain something and compare them and decide on something, and use that as a sort of scratch memory in the same way that we have a working memory. But strangely, we don't refer to that in terms of the neural analogy, which I find quite ironic. I don't know if people are working on that kind of thing. I assume that people are working on everything, but I haven't personally read any work in which the transformer system goes back and edits things in its past context.
Yes.
But I assume that that would be one direction that you might go to try and make the system do something that's more like thinking. I mean, in the end, a purely feed-forward system can't really do anything sophisticated. You need probably to be doing some kind of manipulation, if only to generate internal consistency. So there's no way a large language model can have internal consistency. It's learned everything on the internet. It thinks that the Earth is both flat and round with different statistical proportions. Hopefully most people on the internet think it's round, and that's the conclusion it's come to. But in the weight somewhere is Earth flatness. And so to get to another level of cognition, you're going to need something that builds an internally consistent model of what's out there, whether that needs, as you might argue, interaction with the real world, or whether that can be done purely in the domain of language remains to be seen. But I think that might be one direction that people would take things.
You know, the body of knowledge of humans is a kind of virtual phenomenon that supervenes on all of us physical earthlings. So, like this infosphere that we've created, it's like a symbiotic organism And that has consistent artifacts of knowledge, as you said, but many humans do hold the view that the Earth is flat. So it's just another example of this interesting kind of like levels of emergence.
But they hold an internally consistent view that the world is flat. I mean, as far as they're concerned, it's internally consistent. Obviously, there are inconsistencies that are quite easily proven, but within their mind, they have a model of the world whereby they explain everything. Well, if the moon is flat, well, obviously the sun must be flat as well, and so must. And you know, when you look at the horizon of the sea, it looks flat, and consequently the Earth can't be round. They explain away other phenomena and build up a model that backs up their hypothesis. And there's no sense that a transformer system is doing anything like that. It just starts at the beginning and predicts the next word and has the statistics that are consistent with what's previously in its context window.
Yes. You could argue, though, that humans, our brains are also very chaotic, but we have this confabulation and post hoc rationalization in much the same way. So we, subconsciously we hold conflicting views, but when we try and explain our views and to avoid cognitive dissonance, we try and reduce what we think to something simple.
Right, but we have a finite number of views that are sort of partially rounded theories of the world. The large language model has everything that humanity's ever created, with no preference for one thing or another other than its statistical likeliness. So, so that's still, even if you have multiple conflicting views of the world, there's that famous Walt Whitman poem where he says, do I contradict myself? Very well, I contradict myself. I am multitudes, I am large. That is human beings captured, but we don't have every view on everything simultaneously. We're trying on some level to come up with consistent models of the world, and we need to do that because we need to take actions in the world, and it's impossible to do that if you have 50,000 conflicting views of how things work.
And this is really interesting because Hinton says one of the reasons why ChatGPT is a kind of super intelligence is because it knows all of the things. But I would argue, as you just did, I think, that we are kind of bounded as observers, as there's a computational kind of restriction to how many things a single observer can understand at one time. And we'll get more into this later, but I think with cognition, it's not just knowing, it's also thinking. So just knowing everything isn't actually the whole piece, is it?
Yeah, can you deduce new facts? I think in one of your other podcasts you talked about if you trained ChatGPT with data only up to the early 20th century, would it be able to reproduce the Einstein's theory of relativity? I think we all know the answer to that. It wouldn't.
Definitely not.
And what are the missing pieces? But what that's getting at what I was saying before. It's true to build that theory. You need to have a model of the world, and you need to risk that model of the world is wrong. That certain facts. I don't personally believe you need to observe facts yourself, but certain facts are inconsistent with that theory, and then you need to somehow come up with a new model that itself will make new predictions about the world that people can go and test in the case of physics. But I think that happens on a sort of more minor scale, with your theory about how businesses work or how your friend's personality works and how best to interact with them. You have theories about everything that occasionally break, and you have to radically rethink them.
From a computational point of view, they are finite state automatas.
I mean, you're saying any finite entity can only compute certain things by nature of the fact that it's finite. And
eloquently put. Yeah.
Of course, that is true. But I'm not sure that that's a radical insight. I mean, what would be interesting is if we had some way to characterize what kind of things you could compute with a certain number of parameters or what have you. But as far as I know, we don't really know the space of functions between input and output. We can fully describe, given a fixed set of parameters and a certain neural network architecture, or what lies outside that, because you're building this very complicated surface in multi-dimensional space and everything's dependent on everything else. So it's not really obvious. But it seems it's very rich in that we give it almost any data set we want, and with enough capacity it can fit it.
Well, I think we're just about to put the pin in the middle of the dartboard here, which is that, and we'll talk about universal function approximation later, which is that given an infinite number of neurons, you can approximate a function to arbitrary precision. That's a little bit like saying if I have an infinite size hard drive, I can, store any file that I want to. So the big discussion between connectionists and symbolic folks is the symbolic folks argue that we do need an infinite amount of computation for many things. Neural networks have told us that in many cases, no, we don't. And then I guess it's just about, well, are there boundary cases where we do need an infinite amount of computation?
I mean, an interesting question you're asking in a different way is, are there ideas that the human mind can never grasp?
Or indeed that we can grasp that a neural network can't. Simon, we've now teleported to our studio. We were just outside, freezing ourselves to death.
It is much warmer and less muddy in your studio.
Indeed it is. So Simon, we'll get straight to the chase. I've been reading your amazing new book on deep learning, and I think we should start by talking about the first few chapters really, and in particular chapter 3 and 4, where you talk about not only neural networks, both deep neural networks and just single layer neural networks, but there's this kind of elephant in the room in general, I feel, about neural networks, which is why do they work so well? The unreasonable effectiveness of neural networks. Why do they work so well?
Well, the good news is they do work really well. If you've been asleep for the last 11 years or so, they're incredibly effective, but it is a bit of a mystery, and I think it's particularly interesting to look at it from the perspective of just before AlexNet came out. So ImageNet at that time would have been considered a real stretch goal. Richard Selinsky wrote in the computer vision book he published around that time that he expected it to be years and years before computers could see as well as a 2 or 3 year old. And so ImageNet is a challenging task. The input dimensions, 224 by 224 image, that gives you roughly 150,000 dimensional space. So there's roughly, works out as roughly 10 to the 150,000 possible images. You might say, okay, well, most of those images are noise, but presumably the actual manifold of images is still extremely large. And you've got to build a model that maps this to one of 1,000 classes, and you only have 1 million examples in this 10 to the 150,000 dimensional space. And for each of those classes, you only have 1,000 possible examples. So you can't even build a Gaussian for each class in that case.
Yeah.
So if you didn't know that humans could do this task, you might even just give up. But since we knew humans could do this task, people persevered. And AlexNet set out on this extremely ambitious program that was completely different from what most people were doing at the time. I know that there's arguably some predecessors. I don't want to get into that. I will talk about AlexNet, and you can judge for yourself whether it's the right thing to talk about. So AlexNet sets out to build a neural net with 60 million parameters, several orders magnitude larger than most of the computer vision models that would have been built at the time. And the way that I think about neural networks is they divide the input space into convex polytopes, each of which has a linear, or more properly affine function within it. So if the input space is two-dimensional, then it divides the input space into convex polygons, and each polygon is a sort of plane, and those planes are organized so they make a continuous surface. But now we've got 150,000 input dimensions, so you're in very high dimensions, and we've got this our model makes this incredibly complicated surface, and it's difficult to count the number of these polytopes it creates, but just the fully connected layers at the end would make of the order of 10 to the 4,000. So you've got this huge space, you've got a model with 60 million parameters that creates a number of regions far larger than the number of atoms in the universe. None of, hardly any of those regions are ever going to see a training data point or a test data point at any point during training. And there's some super complicated relationship where you tweak one of your 60 million parameters and these much larger number of polytopes change and manipulated in some very complicated indirect way that's difficult to characterize. So now you come along and say, okay, I'm just going to do a 60 million dimensional optimization problem. At that time in computer vision, people were considered ambitious if they were doing 1,000-dimensional optimization problems. They, typically the biggest kind of problems would have been structure from motion problems. So you would probably try and find the solution in closed form, an approximate solution, and then just use the nonlinear optimization. You're already somewhere near the global minimum, and you're just going to use optimization to get to the final place. But they're going to start by just randomly initializing this network and then using the dumbest algorithm, basically noisy gradient descent, to get to the bottom. Because you can't use anything else, because everything else uses second-order information, and now the number of parameters is too enormous.
Sounds like a disaster.
It does sound like a disaster. I don't think many people would have predicted you could even learn the model. But one thing they have in their favor, and we can come back to this in a bit, is arguably there are far more parameters in their model than there are data points. So it's over-parameterized, and perhaps that makes the fitting easier. And there's a subtlety there that we can come back to.
Yeah.
Okay, they fit the model, but as I said, there's 60 times more parameters than there are data points. So the surface they fit basically goes through every data point exactly, but for every data point it goes through, it can do 60 other things. It has 60 more degrees of freedom. So between those data points, which, as we've discussed, is almost the entire of the space, it has latitude to do whatever it wanted. And actually, they had applied some regularization and some dropout, but subsequently we found that those aren't really critical to this. So at the time, you might have explained it away with that, but since then, we know we can learn models without dropout and without regularization, and they still generalize reasonably well.
Yeah.
And somehow this model performs 15% better than the next best thing, or whatever it was. Quite surprising. I mean, jaw-dropping, really.
Yeah. Well, so let's do a point of order just on that then. So first of all, I'm a huge fan of this view of neural networks that you've just spoken about, which is that essentially it slices and dices the ambient space into these locally affine polyhedra. And Randall Balistriero came up with this spline theory of neural networks, and folks should watch the first Lacoon show where we spoke about that in detail. And what he basically said was that for a given input example, the neural network can be represented with a single affine transformation, which is surprising to a lot of people for two reasons. First of all, people think of neural networks as being, non-linear. And also it gives this beautiful intuition of neural networks as being a collection of storage buckets, not too dissimilar to a locality-sensitive hashing table. And I think that's very instructive.
Right. And so I wrote this book blissfully unaware of that theory, I should say, but that's pretty much exactly how I describe it in this kind of simple, constructive way. How do we combine together these networks? We should say that this is only true for ReLUs and leaky ReLUs and parametric ReLUs. If you have smoother functions, then you can no longer characterize it in this way. But actually, I like discussing it in terms of ReLUs because then the number of output regions gives you some notion of the complexity of the output surface, whereas once you start talking about smooth functions, it's much more hard to characterize that.
But it's kind of locally smooth, because I guess for the folks at home, every single one of these neurons, will maybe come back to that, it's kind of like a hyperplane. And so you train the network and you move all of these hyperplanes around in the ambient space. And essentially, when you put an input in, it's kind of activating some of those hyperplanes, and it's creating this kind of convex region.
Right, according to which hidden units are active or not active.
Yes, and even though these are piecewise linear functions, there are so many of them kind of like, densely overlapping each other in space. They appear locally smooth.
Presumably. Well, we can plot like one-dimensional plots through the function and see what it looks like, and of course it does look smooth because of the sheer number of them.
Right, but then we get to the next interesting bit, which is, so you spoke about overparameterization and, finger in the air, let's say that there's an exponential number of these convex polyhedra, something along the lines of, I think you said 2 to the power of the number of dimensions. And
well, generally it will be more than that. I was trying to give an utterly lower bound that nobody could disagree with.
But this gets to the fascinating thing. So traditionally, before neural networks, the world was different, and we used to talk about the curse of dimensionality, and that's basically this statement that there is an exponential relationship between the volume of the space and the number of dimensions. So
yeah, I would say it's the tendency of the volume of space to completely dwarf the amount of data you have as the number of dimensions goes up.
Exactly. So when the volume of the space does increase exponentially, the statistical significance of your training data kind of tends towards 0. So there is no statistical information anymore, which begs the question, if there's no statistical information, how do the networks work?
And now we're getting to the difficult part. Why does it generalize in any way?
Yeah.
It's clear that it can pass through every data point.
Yeah.
But what it does between the data points is, in some ways almost happenstance. It's a byproduct of our algorithms. It makes some smooth interpolation. Why that's a good smooth interpolation, we don't know. Why it even becomes smooth, we don't know. It seems like it's some complicated byproduct of the way we initialize the neural networks, the noisy algorithms we use to train the neural networks, the overparameterization itself. Perhaps what the kind of thing that might be going on is we wind up with smooth networks that interpolate just because we overparameterize so much that when we set up our networks, we initialize them, and the wider they are, the smaller numbers we put in. And the numbers start small and they stay small because it never has any impulse to make them larger. And because the numbers in the network have small magnitudes, that basically maps to small slopes. I want to slightly come back to the overparameterized thing as well, because it's not totally obvious to me that everything is clearly overparameterized. So while AlexNet had 60 million parameters and 1 million training points, they also augmented their data by a factor of 2048. And if you look at all of the papers pretty much on this ImageNet classification problem, they're all sort of overparameterized by the best results from the last 10 years by sort of 10 to 100 times. But they also all augment the data, which muddies the water. So it's... one way of thinking about it is that it's more data points and we're not overparameterized. But of course, they're not independent data points anymore. They're translations, rotations, color transforms of the input image. So I don't really quite know where we are with overparameterization.
Yeah, well, I want to get to the inductive priors in a minute, because I do think of these local affine polyhedra as being buckets. And then we get to, well, if you perform some semantically equivalent transformation like a translation or a rotation, as far as the MLP is concerned, it's a different thing. So these inductive priors basically photocopy the information so that you're putting the same thing in different buckets, so that you're kind of like cheating. Maybe we'll get to that in a sec, but just to finish the loop on this generalization thing, what we're doing is we're complexifying the neural network. And this is really weird, because we were taught in school that Occam's razor is, like simple things generalize. And now we are exponentially complexifying the networks. Why do they still generalize?
Well, it's interesting how the theory can't really cope with that. So previous ideas of theory like Rademacher complexity would have predicted the opposite. It would have predicted that as we added more parameters, the generalization would have got worse. I mean, the kind of loose idea people have when they talk about double descent and stuff is there's more regions just means that you can model a smoother function. It has to go through the data points and it's smooth elsewhere. And we don't have a much better conception of it than that. For things like images, we can put in some prior knowledge about images that the statistics are the same everywhere, use convolutional networks. So we're searching through a more sensible subset of models. Convolutional network is a sort of strict subset of a fully connected network. So we're searching through a more sensible set of models that have some prior knowledge we put in, but that still doesn't really, in a satisfying way, to me, explain why networks generalize so well.
Can we bring in this notion of the manifold hypothesis? How does that? Because even before you were saying something really interesting, which is that everything's an inductive prior. Even the world we live in is an inductive prior, but just keeping the philosophy out of the discussion, data is definitely an inductive prior. So you can do data augmentation and you can kind of oversample effectively, in the vicinity, or you can tell the neural network that doesn't know about certain types of transformation. You can kind of effectively tell it that the transformation exists by augmenting the data.
Yeah, well, there's two ways. You can build that into the networks as equivariant or invariant according to your needs, or you can just blast it with data. Either transforming the output in the same way you transform the input if you want it to be equivariant, or ignoring the transformations if you want it to be invariant, that kind of transformation.
Yes, and there's an interesting relationship because we've got this bias variance trade-off, and we're doing statistics here. So in an ideal world, you would only need to give it one labeled example of the thing that you want to learn because the network would understand all of the transformations that can happen. That doesn't work. So there's a middle ground between, on the one hand, we have this dumb MLP that knows nothing, and we're kind of introducing all of this, what would you call it, physics, domain knowledge of how things can be transformed.
Domain knowledge seems a good term, yeah.
Yeah. Okay. Interesting. So we were talking about this manifold hypothesis. So that's this idea that there's some kind of a subspace in the data, and because theoretically, as you were saying earlier, according to the curse of dimensionality, it should be physically impossible because you would need more data points than there are atoms in the universe to train these models. So people cite the manifold hypothesis, which is to say there's some kind of subspace in the data where the network can kind of focus its attention on. What do you think about that?
I mean, in some case, there's a very simple case where you can almost describe that subspace, which is if you take somebody's face and you film them in fixed lighting from a fixed viewpoint and they don't move too much, then they have 42 muscles in their face and there's only 42 things that can happen. And that's a very sort of physical description. Of course, the real world's more complicated than that, but there are still regularities. There's only certain kinds of materials out there. There's only certain kinds of lighting. Real images are not all images. Go randomly select pixels and you see how many times you have to do that before you get something that doesn't look like noise. You will give up very quickly. We don't really know the size of that manifold, though, although you can estimate it because it's connected to the degree to which you can compress images. And so one thing that's really interesting to me about these new diffusion models is that they're not that big. You can put them on your hard disk, but yet they seem to be able to generate this incredible array of images. So that we don't know what images they can't generate, of course, but a good portion, apparently, of the image manifold can be put on a hard disk, suggesting it's not actually, the space of natural images is not actually that large.
Yeah, interesting. So you're saying the apparent creative and generative ability of these models suggests that there is some low-dimensional manifold of images.
Yeah, well, there must be, because we're not, the generative model does not have 10 to the 150,000 parameters. For the very good reason that, we can't store even a tiny, tiny fraction of that.
Very interesting. Okay, so we should speak quickly about this universal function approximation. So if we start first of all with a shallow network, this universal function approximation theory basically says that, if you approximate it to arbitrary precision, you can, represent any function. And it's just a collection of basis functions, right? We're just optimizing the placement of these basis functions.
Yep. I mean, you can still think about it just dividing the input into convex polytopes too. That's fine. Or you can consider it in terms of basis functions.
Right. So I've always thought that this universal function approximation theorem isn't particularly useful.
I mean, it is important that we know that you can represent, with some caveats, you can represent any function you want to. What's really interesting is that to build anything that works really well, we seem to need 10 to 12 layers. And it's difficult to know, and there are quite a few different theories why we would need a deep network, given the universal approximation theorem says a shallow network can model anything.
Well, I mean, just to have a go at that. So that theorem is talking about a very wide single layer neural network. And it seems to me that just placing basis functions on a single layer of a neural network, it's almost antithetical to generalization. It is memorization by definition. So you make this really interesting argument in your book that when you introduce depth to a neural network, what you're doing is you're kind of progressively refolding those affine regions, right?
Yeah, that's one partial way to think about it. So partial way to think about it is that if you have a two-layer neural network, the first network can be thought of as folding and replicating the second network in a complicated way. And go look at a picture in my textbook. That's difficult to describe verbally, but that's only a sort of partial way of looking at it. There are other ways of looking at it as well. Like a different way of looking at it is that you're creating, I think, what you would call increasingly complicated basis functions, and then you're clipping those and recombining them to make more complicated functions still. And so one way sort of emphasizes this symmetry and this folding that is going on, and another way emphasizes this sort of clipping and creating more joints. In one dimension, they would just be joints in a function. In 2 dimensions, they would be sort of one-dimensional folds in the function. So that's a different partial way to look at it, but I don't think anyone, even for a 2-layer network, it's really hard to get a full picture in your mind of exactly what it's doing. But what's definitely true is there's now like a really complicated relationship between manipulating any one of those parameters and the whole surface that comes out at the other end.
Yeah, and when we did our first show on spline theory, we were showing this neural network visualizer, and you can add layers in and you can change the activation functions, and it kind of shows you the activation space. And very, very quickly you get these very complex behaviors emerge where the hyperplanes kind of cancel each other out. And what you were just saying there that I want to get to is this topological interpretation, which is to say that as you complexify, as you go through the neural network in successive layers, you can recompose all of the prior neurons in previous layers that are topologically addressable. And this is a DAG that we're working in. So that's obviously a subset of those. And there's this really interesting thing that the neural network has a structure which is kind of defined by the early layers. So as you go through the neural network, it's kind of somehow constrained by what went before.
I mean, it's constrained in terms of information. If you lose information at the start, it can't be recovered. But I think you're trying to get at something else.
Well, some of it is to do with how flexible, like there's a continual learning dimension to this, which is to say early on in the neural network, those initial basis functions are making chops in the space. And then the way I think about it is all of the kind of complexification that happens later is kind of working inside those early regions. So it's almost like it's becoming more and more entrenched in what it does as you go through the neural network, which is to say that it becomes harder and harder for it to completely learn things differently.
I think, I mean, I'm trying to interpret the way you're expressing this, but I mean, perhaps what you're trying to say is that it's sort of collapsing bits of the space on top of itself and then treating those similarly, and it can't then uncollapse them. So, and that might be how you could exploit irregularities in data. That's one interpretation, but the mirroring, I think, actually kind of happens the other way round, that the early, maybe I misunderstood how you said it, but the early layers are defining how the mirroring will occur, how these reflections will occur in the later layers. So really, it's in that view, it's the later layers that are sort of defining the structure, and the early layers are then propagating that structure to different, and reflecting it like a crazy house of mirrors into the rest of the space.
I mean, I guess like one way I think about continual learning is the extent to which you could destroy a neural network. Let's say you take GPT and you just start fine-tuning it on noise. And what would happen? Would it very quickly forget everything it learned before, or would it just refuse to budge?
Well, that's a complicated question that would depend on the learning rate. And these transformer models are quite interesting because they generally, as I understand it, and please correct me if you think I'm wrong, I don't think they train them to zero training error. I think they generally do one pass through their training data and stop. So,
3 or 4,
or 3 or 4. So it's sort of, to some extent, probably remembering what it saw recently more than what it saw a million tokens ago, or a trillion tokens ago, whatever it is. How quickly, if you added noise, would it decrease? I mean, it really, So what have you done by adding that noise in? You've changed the whole loss surface, because now the loss surface either only includes the noise, or I'm not sure you're suggesting if the noise is added in with the real data. But either way, the loss surface is now different. And you're heading now downhill from what used to be, I'm going to loosely say, the global minima, and I'll probably say that several times during this, but I mean the sort of level set of good solutions that that fit the data well. So you're now heading downhill from that point, which is raised up in your new loss surface. And how quickly it will forget just depends on the learning rate and the new shape of the loss function. So I don't know if you could say anything definite about that.
I guess I was coming at it from, Chomsky says that we see the world using our native priors. And in a sense, neural networks are the same. You look at a vision network, they have these Gabor filters that are baked into the early layers. And to a certain extent, after a while, the neural network only sees the world in terms of its fundamental basis function.
So I don't like that idea of considering you say these Gabor filters are baked into the early layers, and I would push back on that a bit. What people are saying when they say that is that this neuron has a high activation when you put in this kind of thing. And to some extent, that's sort of trivial. You've made some small set of basis functions because this network at this point only sees a 7x7 patch of the image or something. And just because it reacts very highly to that particular thing, it also, if it's not the first layer, if it's in a few layers in it, it's going to react in a complex way to lots of different things. So what you're trying to do is you're trying to characterize this very complicated multi-dimensional polytope by one point that looks like a Gabor filter, but really it's this incredibly complicated shape in 150,000 dimensional space. And so I don't like the idea that you're going to say, oh, well, we can characterize that shape by this one point.
Yeah, no, I think you're absolutely right there. So that is a mistake that we're looking at interpretability methods, which grossly simplify a neural network, and we're kind of making statements based on that. So I think you're absolutely right about that. But there's also this interesting dimension of training versus inference. So it has been said that over-parameterizing is something which is helpful for stochastic gradient descent, but I would like your viewpoint on the extent to which we need to have all that representational capacity for inference. So do we need to memorize all that stuff, or could we actually strip it away?
Yeah, so it definitely makes it easier. Terry Sinowski has this beautiful expression where he says, it goes from searching for a needle in a haystack to a haystack of needles. So you wind up with this loss surface where there's a very high dimensional part of that loss surface that is the global minimum, by which I mean a good level set of solutions that fits your data perfectly.
Yeah. I have a feeling, and I know that you're going to push back on this, that there is an inherent model bias in neural networks, which is to say a lot of these inductive priors and training tricks and so on, they're ways of making the network focus on the modes in the data, the areas of regularity or where most of the variance is, and all of the low frequency attributes. And just to be as clear as possible about that, I mean things that don't happen very, very often. They tend to be snipped or ignored, or they're not learned. Is that something fundamental, do you think, to neural network?
So I think we do need to fit the data perfectly or close to perfectly. So for our training data, we always get the right output, because ultimately these things are quite stupid and there's nothing much they can do apart from interpolate smoothly, and I'm using the word smoothly very vaguely because it's difficult to characterize exactly how they interpolate between them. And I'd rather interpolate smoothly between the correct, true data points than a neural network that missed those in the first place. How could that be better not to memorize the data?
So I have a feeling this is a story of the tyranny of metrics, which is to say we optimize on accuracy, and the neural network, I assume, would learn that, well, given that this is such a long tail, high entropy thing, it's probably better that I just don't bother learning it than get it wrong all the time by trying to learn it.
But I think it does learn. It does learn from most data sets the long tail of the data you give it, because the loss comes almost zero. So for a regression model, the loss can literally become 0.000. For classification models, it's a bit more complicated because you're trying to push these softmax functions to infinity, so you never get there.
Training loss, though.
Training loss, yes.
But that is not going... So I guess like those things are like atoms in the universe, and even though the network knows about them in the training set, they would never have any statistical power.
So that wasn't a question.
Well, no, I'm just testing the principle. But I guess we'll talk about ethics and bias and fairness later on. But it's really difficult with a single training objective to square the circle, to have high accuracy and high fairness.
Yeah, absolutely. I think what you're worried about is areas of the data space that represent perhaps minorities of individuals, and particularly intersections of those minorities, where perhaps gender and race or what have you, and so you wind up with a very small number of training data points. And I think it's a question of whether you're attributing the failure to generalize to that to the neural network, but that might be unfair. Maybe the failure to generalize that is that there is literally not enough statistical regularity in the data you've given it for it to possibly generalize.
Interesting. Okay, well, just to close the loop on chapter 3 and 4. So there are some other things that we tweak in neural networks, like the initialization, things like the learning rate and which activation functions we use and stuff like that. So can you sketch out some of that?
So I think it's interesting to think about that through the lens of either learning or generalization. So we've learned quite a bit about which things affect learning and which things affect generalization. Surprisingly, the data set confusingly doesn't affect the learning so much. So you can randomly perturb the labels.
Yeah.
and the neural network will still learn the training data fine. Or you can shuffle the input pixels of images, the neural network still learns the training data fine. So there are some things you'd be really surprised about it can learn, despite that the neural network will learn despite those factors. Also, other things in terms of learning.
Could we just pause there, because that was a really interesting bit, which is that, and we'll show an image in your book. So there are two curves, and one curve is when you're just memorizing essentially random information, and then the other curve on the left. So the kind of the horizontal distance between those curves is the generalization gap. So on the other curve is where you have the actual data with the actual labels, and then there's another curve in the middle where you have the actual data but with random labels. So I guess like the first intuition is, isn't it interesting that neural networks don't struggle much more to learn completely random data?
So this is a famous paper from Zhang et al. 2017, and it shows that you can perturb these labels, or you can shuffle around the input data in various ways, and it still learns perfectly, but it learns more slowly. So, but that might just be because there are regularities in real data. So you move the surface up, and it naturally fits through several data points, and now it has to contort itself more to fit completely random data. So I don't think the length of time it takes to fit it is really significant. But it shows how incredibly flexible the model is, that you can throw at it any data and it will fit it and interpolate between it. It's just that the interpolation is meaningless if the labels had no information in them.
Yeah, it's interesting that you say you can't intuit how difficult a problem is by the convergence time.
The convergence time depends on a lot of different factors, but one of the main ones is where you initialize the parameters. So we initialize the parameters for very practical reasons to certain variances, because if you don't, you get exploding gradients where, for people who don't know about this, essentially the numbers in your neural network, the activations and the outputs, start taking wildly large values, and you can no longer represent them in finite precision floating point numbers. Or if you don't set them correctly, they wind up being too small, and we call that vanishing gradients. But it's referred to in terms of gradients, but actually it happens in a forward pass through the network as well. So we have very practical reasons for initializing our networks where they are, but actually that also depends, we still have a range of values we can set it to, and it still works without breaking reaching the limits of the computer's precision. But actually, the magnitude you set the weights to drastically determines the training time. So, and it also determines generalization. So there's a sort of Goldilocks zone, they call it, not too big, not too small, just right, of parameter magnitudes that seem to give the loss functions sensible properties, positive curvature where you want positive curvature. And I think that's pretty easy to understand, that if all the parameters are too small, then it can only create very flat. Loosely speaking, people who really know what they're talking about are going to take offense to this, but loosely speaking, if the parameters are very small, it makes very flat functions, and maybe your function isn't very flat. And if the parameters are really huge, then it has functions with big, sharp changes. And you don't want that, because maybe your data is quite smooth. So it takes longer, if you don't initialize the parameters correctly, to kind of reach the presumably reasonably smooth pattern of your data. And of course, that also speaks to generalization, because you want it to interpolate smoothly between your data. So you don't want wildly varying large parameter values that cause big fluctuations between your data points but still fit the data points. So the time it takes to train depends on the initialization as well, but if you give it enough time, it seems to get there. In terms of generalization, there's a phenomenon connected to that called grokking.
Yeah, I had Neil Nanda on.
Did you?
Yeah.
So essentially you can get cases where it fits the data perfectly quite early on, But then it takes ages and ages, and suddenly it generalizes. And
Yeah.
this has been interpreted, or my best knowledge of the interpretation is that this is what happens when you set the magnitude of the parameters wrong. What's happening is it's fit the data correctly, but it is wildly varying between the data points. But something in our methods for training, presumably some feature of stochastic gradient descent or some other explicit or implicit regularization that you've put in there, is causing the network, the solution, even though it already fits the data, sort of traverse this loss surface. It's not at the minimum, it's in a family of minima, and it's traversing through that family until it eventually gets to something that's smoother and interpolates well, and then it generalizes. But exactly why it should move through this surface to something that's smoother is, again, quite complicated and subtle.
Yes, I mean, yeah, folks should definitely check out the Neil Nanda episode. But yeah, it's, as you say, there's this phase change from memorization to sudden generalization. I think Neil did say that it's a bit of an illusion and people slightly misinterpret how it works. And as you said, we're trying to design the loss surface to be as smooth as possible. And I think his original paper was on modulo division, which is not very natural, because I guess part of why it's possible to coax the loss surface to be so smooth and interpretable is because of this natural data thing as well. So maybe an artificial data set like that wouldn't be so amenable, so you would get this sudden grokking later.
Yeah, perhaps. You mean that the easiest way to fit it is sort of with some function that, yeah, there's no natural smoothness to it, and consequently you wind up fitting it with a very complicated function with a lot of variance between the data points, and then it takes a lot of regularization and rambling over this loss surface until we get somewhere sensible. Whereas for a more typical data set, you naturally wind up with a sort of smoother surface to begin with. I mean, that makes sense to me.
Yeah, but it is one of the crazy things about deep learning, which is that, and grokking was a surprise because most of the time, it's like cooking. The secret is in the preparation. So you kind of massage the loss surface, and then you just know, you can almost predict, just like OpenAI could predict how much training was required to get GPT-4 level perplexity. You know, there seems to be a regularity in terms of, okay, it's going to converge, and because it's over-parameterized and finessed in a certain way, it's going to converge in a certain amount of time. It's going to have a certain shape to it when you train it.
Yeah, I mean, the most recent paper that I've read on this, and you should understand that I'm very much like ChatGPT. Every time I finish writing the chapter of a book, I stopped reading, because if you don't stop reading, you'll go crazy. There's, 4,000 papers coming out every month, and you can't possibly keep up to date. The most recent paper I read on this was called OmniGrok, and basically it says that time is predictable because the magnitude of the weights are gradually decreasing at some fairly constant rate, and eventually they come into this Goldilocks zone where things generalize well, and that's when suddenly the generalization performance improves.
Cool. Now, the book makes a really, really huge effort, I would say, to visualize things in images and low dimensions. What was the thinking behind that?
Well, I think people learn in different ways. So I try and have 3 ways to understand everything. There's textual descriptions, there's equations, and there's pictures. And so to me, the mental process of connecting those things, which you sort of actively have to do if you read the book, leads you to a deeper kind of understanding. A lot of ideas, even diffusion models and GANs, can be drawn in 1 or 2 dimensions, and you can really effectively convey these concepts in a non-technical way before you hit the equations, which is good for learning. But you also have to be a little bit careful, because multidimensional space doesn't quite work in the way you expect it to. There are a lot of strange phenomena. So if you take 2 random points that are Gaussian distributed, after about 100 dimensions or even less than that, they're almost certainly orthogonal to one another. A famous one is that a hyper-orange, a multi-dimensional orange, basically all of the area is in the skin and none of it is in the pulp. Yeah. Or my favorite one is if you take a multi-dimensional sphere of diameter 1, a hypersphere, and you embed it in a multi-dimensional cube. You can imagine in 2 dimensions you've got a circle, in a square, in 3 dimensions you've got a cube, you've got a sphere in a cube. As that goes to infinity, it turns out, as the dimensions increase, it turns out the proportion of space the sphere takes becomes 0. It's all in the corners.
Yes.
So I draw these pictures in...
It's like the question of dimensionality again.
Yeah, I draw these pictures in 1 or 2D. You know, I like to joke that's because MIT Press wouldn't give me a budget for a 5-dimensional book. I asked for it, but they stuck with 2 dimensions.
Yeah.
But you should be cautious. But having said that, I don't think it's necessary to work in the super high dimensional spaces we work in to see the phenomena of deep learning. And there's a really interesting data set that I use a lot in the book called MNIST 1D. So our simplest data set is MNIST. It has some disadvantages in that, for example, we're too good at solving it now to really demonstrate much on it. But this makes an even simpler data set, and basically what it consists of is 40-dimensional data. It's just 1-dimensional data, and they start with a template that looks a little bit like one of the 10 digits. So, for example, the 0 has 1 bulge and the 8 has 2 bulges, and they find a way to, actually it's one guy, Sam Gradanis is his name, and the paper's called Scaling Down Deep Learning.
Oh, right.
Completely against the prevailing winds of deep learning, which are to scale everything massively. And then that is translated. So it's a type of data that's amenable to convolutional networks, for example, because there's a dimension that you can be equivariant or an aspect of it you can be equivariant or invariant to, and adds various amounts of noise. And it's completely procedurally generated. So you can generate any amount of data with any amount of noise. And the interesting thing is, even though this is only 40-dimensional, most of the kind of epiphenomena of deep learning can be seen. So you can show adversarial examples, you can show lottery tickets, you can show double descent, and you can do all of this. You know, this is now an aside that you don't even need the GPU. You can just run it in your local Python window on the CPU. And I think this is a really interesting data set. So the actual huge experiments we're building, and we're now building things that's sort of the order of the complexity of a human mind. And I come from biological sciences background, basically, and if you want to try and understand that, what you do is you go out and you collect a data set as thoroughly as you can, along as many dimensions as you can, and then you go away and try and come up with a theory that explains that data set. So in this case, when is it trainable? When is it generalizable? And here we have a data set where in theory you could do that. You could train many different networks, varying all the parameters, because it's very quick to train. And then you could try and properly come up with a theory that says, okay, when I've got this kind of data with this amount of noise, these statistics, these are the networks that will work. These are the networks that will train. These are the networks that will generalize and have proper, tight bounds on those things. So to me, this is a really interesting data set that could be a test bed for actually understanding deep learning better, but which is currently not used at all because you can't publish a paper unless you get state-of-the-art on some enormous data set with millions of examples in it.
Yeah, because we were going to talk earlier about the alchemy of deep learning, because we don't really have any overarching theories of deep learning. I mean, there's things like NTK, and we spoke about spline theory and stuff like that, but there's not really much, is there?
There are bits and bobs. A lot of it relies on unrealistic assumptions. Some of it often relies on the network being infinitely wide, which actually I'm less worried about those ones, because infinitely wide probably means somewhere along the way you're relying on the central limit theorem, or the law of large numbers, either of which probably converge a long time, to something like a Gaussian or the expected value a long time before you really are infinite. So those ones I'm kind of okay with. The ones that rely on, the network width being the square of the number of data points or something, that starts to worry me, because that's sounding like it's an argument based on some sort of combinatorial geometric argument, and that really might need that true number to work. There is a history of the experimenters rushing ahead, doing things, often introducing components to our networks, which definitely empirically help, explaining them in some way, and then later on when we go back and look at those, it turns out they don't do exactly what we said they would. And the theory people lag a long way behind. Some interesting bits of theory, I think, are neural network Gaussian processes. Yeah. You mentioned NTKs. They're sort of, I think of them anyway, as the Bayesian version of that. Yeah. And so they can predict some things about trainability, but largely they predict things about trainability that we already knew from experimentation. So, and they've, using some of that, they have built networks with thousands of layers, but those networks with thousands of layers don't get cutting edge results. So you have to wonder, had the experimentalists already discovered this, but then they can't get a paper out of it, so they just throw it away.
Yes.
So not to knock that work, I think it's really interesting, really important, but just to say it lags behind. And we're in this weird situation where a whole bunch of the apparatus we've put in to make networks work doesn't do exactly what we think it does. So when you first learn about stochastic gradient descent, you're taught that the reason we put it in is so you can bounce over local minima, perhaps, into another valley. Yeah. But that turns out to be absolutely nonsense. I don't think that's what's happening. You can learn quite large neural networks with enormous batch sizes, so not much randomization, or sometimes even full batch, and it still gets to the bottom. So why do we still use stochastic gradient descent? Number one, it's fast. You're only using a subset of the data points, and if you've got millions of data points, that saves you a lot of time. Number two, it seems to have some regularization effect, and you can actually characterize that, and there's a section in the book about implicit regularization, so you can show for finite, basically it's the difference between it taking these small steps, which you would call gradient flow, and finite steps. And once it starts doing that, and combined with the stochastic element, you can show that there's certain regularization expression that you can write in closed form that you're effectively adding to the loss function. And so the whole learning takes a slightly different trajectory and gets to the bottom in a different place. Like another example of experimentalists sort of rushing ahead would be batch norm, which has like a really peculiar history. So batch norm...
Is that Goodfellow? Well, no, is it Segedi?
Segedi,
yeah,
I think,
I had him on the show, yeah.
Batch norm was introduced originally to tackle something called covariate shift, which I'm not sure I totally understand it, but I think basically the idea, you can correct me if I'm wrong here, is that after you've adjusted the parameters in the later layers, the changes to the parameters in the earlier layers no longer make any sense, which from a pure mathematics sense doesn't make a lot of, is not understandable, but I guess it's to do with the fact that you're not actually taking infinitely small changes, you're taking finite changes. But subsequent experiments have showed that you can introduce covariate shift and it doesn't help. Yeah. And batch norm was later adopted because after they figured out how to stop exploding gradients and vanishing gradients, they developed residual networks, and that put those problems back in. And batch norm resets the variance and consequently stops gradients exploding. So it found a use, but then it turns out, but there's other ways to solve that problem. You can solve that problem by just resetting the gradients without taking into account the batch statistics. It turns out that it has a regularization effect because it's basically adding random noise. The batch is slightly different each time. It also has more complicated effects where it allows one bit of data to sort of leak information to another, because one can have a really enormous value, which makes the batch variance large, which then shrinks the other variance at the other one. And that's why they don't use it in transformers with where you're using masked attention, because the whole point of that is that the words further along in the sentence don't the words don't have access to the data further along in the sentence. You're sending this all in the batch, so they use layer norm instead. So batch norm is an example of something that was introduced for one reason, adapted for another reason. It has it's now kept in there, or some form of it is kept in there because it has this indirect regularization effect, and it also has some positive disadvantages that have caused it to have to be adapted in certain circumstances.
Yeah, but I was going to make a comment that if anything, as time has gone on, we seem to have less reliance on some of these tricks and almost more focus on just big models, more compute, more data, and so on. Do you think there's any truth to that? Or because you just said yourself that in many cases, people don't even understand exactly what the effect of this thing is. When they do ablation studies, they tend to learn, actually, this thing wasn't needed after all. And is there a trend towards simplifying the process?
I'm not sure there is a trend towards simplifying it. I think there should be a trend towards simplifying it. There's a great paper that came out in around 2020 where they analyze all of the things that have been done to transformers actually scientifically in these different papers and find that hardly any of them make any difference.
Yes. Yeah.
And so, it's tied to our obsession with state of the art. You try all of these different things and then you don't interrogate too closely whether this particular activation function really was critical, because now, it's 2 days before the NeurIPS deadline and you've just got the state of the art and so people, and then no one ever gets around to going back and looking at these things. But I know when transformers were introduced, they were super complicated to train. You had to use this thing called learning rate warm-up. There are very complicated effects of where you put the layer norm, what happens with the variance in the residual layers, the difference in the size of the parameter gradients as you go through this softmax function versus the path that computes the values versus the residual. You got 3 parallel links. And they were super hard to train, and they relied more on training things. But actually, the sort of state-of-the-art training transformers, which I guess is sort of what you're implying when you're talking about very large models, I don't know if they've eliminated. I just don't know the answer to your question.
Yeah, I mean, it's related to this graduate-student descent thing that we've been talking about in general. And I mean, I was speaking with some folks at NeurIPS, and I mean, Hinton, for example, was always a big fan of contrastive learning, where you kind of like, you contrast an image to all the other ones in the data set. And then I think LeCun at FAIR kind of pioneered this non-contrastive approach, which is where essentially you kind of I think like similar to Siamese learning, but you mutate pairs of images. So you're kind of like pushing images off the manifold rather than comparing them to everything else. And there are so many variations of that, like Barlow twins and, God knows what else. It's been a while since I looked at it. But these things are all just millions and millions of minor engineering variations on an idea.
Yeah, and it's interesting that this is now what we take to be results in a scientific conference. We don't necessarily value insight. There are papers that are searching for insight, but it's a smaller community that is lagging behind. And I mean, personally, it's part of the reason why I stopped doing experimental research was that I really love the ideas and I really love trying to understand what's going on, but it often takes, graduate student dissent. It takes the supervisor to, an afternoon to come up with an interesting idea, and then, 20 minutes to persuade the graduate student it was really their idea. And then PhD supervisors, you know what I'm talking about. And then off they go for like 6 months experimenting to get the criteria they need to get into the conference. And I don't think that's a good use of scientific time or public money. That's probably a good use of Google's money and OpenAI's money, but is that a good use of Stanford's money? Maybe not. Maybe they should be doing something that's a bit more scientific and that has some genuine insights, not trying to push this benchmark by another 0.1%. Because often it's just sort of chance as well. There was just a couple of weeks ago, there was a paper that argued that actually ConvNets do just as well as vision transformers on or certainly comparable to the best vision transformers on the ImageNet classification task. It's just no one's ever pre-trained them with Google's enormous training database before and deployed them at such enormous scale. So we can't even necessarily trust all of these results. I mean, we can trust them in that, in 99% of cases, they did what they did and they got the results that they got, but we can't trust that the scientific conclusion that vision transformers are way better than convolution until someone's properly done some science to do a exactly comparable experiment. And we're not very scientific community. We've got better in the previous decades. It was crazy. People would make claims. They'd say, okay, I've invented this new method, but actually they'd changed like 7 things. And the new method would often not be the thing that made the performance gain. And we've got slightly better because now we do ablation studies, and but we're still fundamentally not very scientific. Where these are people who are trained as engineers, not scientists.
100%. And even when they do ablation studies, it's very expensive, and it's now become a game that only the top players can play. And OpenAI, for example, I mean, they've done some very cool research over the years, about scaling laws and RLHF and, CLIP and GPT and blah, blah, blah. But, ultimately, and I don't want to sound cynical, but the success of their methods is just so much data. They've built a Google vNext organization. They're hoovering up all of this data. Yep. And I think a lot of people underestimate how valuable the data of people using ChatGPT is. So they're hoovering data.
Oh, absolutely. There's a reason why they let people use it for free.
Oh, 100%. So it's like it's one step away from a mechanical Turk. So in the background, they're just generating more and more data. And they've cultivated this image that they're doing science. And for reasons that we've just discussed, I think they're doing engineering. And I think I'm really looking for something different now.
Yeah, I don't mean any disrespect to the engineers. It's no doubt incredibly difficult to engineer ChatGPT on that kind of scale.
Yeah.
But again, it's not very intellectually satisfying sometimes, those papers. There's not many insights that you can get from them other than, I suppose it's really interesting that you keep adding data and it does keep scaling. That's not something we necessarily would have predicted, and so that the amount of data perhaps will be the limit on these kind of models. Not even computation or model size, will literally be the amount of data that you can hoover up off the internet. We'll see what happens, but there's not many insights. And I would like to reiterate that you can get most of the interesting phenomena of deep learning in 40 dimensions. And so if you want to do science or you want to try a new idea, don't even try it on MNIST. Try it on MNIST 1D. And if it works there, then try scaling it up. And if it's not an interesting idea, when you try it in your tiny data set in 40 dimensions where no one cares what the state of the art is, then is it worth writing a scientific paper about it?
I know. I think one thing that happened with GPT is that it transgressed the uncanny valley. And, we were talking earlier about how people psychologize and use all of these other adjacent mental frameworks to understand what's happening. The reason why people are so excited about the singularity and AGI and all of this stuff is because we've got this artifact now, which is remarkable. And it's just memorized all of the data on the internet. And I think that there's more to cognition than just knowing, just being able to retrieve information. I think it's something that is very, very good used interactively by a human. So I'm using it like I would use Google, and I'm searching for information, and it's doing things which are remarkable.
But in some ways, you're still the intelligence there. It's what you're asking it. That's the interesting thing, not the way that it responds.
100%. And that's why when you set it up in an autonomous arrangement, so something like AutoGPT, or even getting it to do something on a schedule, the magic disappears. It's like this uncanny valley, or like the suspension of disbelief or whatever. It just instantly disappears, and it does stupid things, and you think, oh, I can't believe I was fooled by that. I was fooled by randomness. There's like the UX and the fact that it's an extended mind. It's what David Chalmers and Andy Clark called an extended mind, essentially. So it's like a cognizing element as part of my physical process of cognition. But so many people are kind of taken in by it in that weird way.
Yeah, I think you have a more. I think you have a higher opinion of it than I do. Like, my experiments with it haven't been super successful. I've asked it repeatedly to generate a story, given a few premises. It almost always generates the same story with even the same name of the protagonist. And it knows really well about some things because there's a giant corpus of data on, and unfortunately it knows really well about the things that computer scientists know about because they are present in abandon on the web. So if you want to ask it about search algorithms, it really knows about search algorithms, and it can write code for them because is repository after repository implementing different sort code algorithms. But once you get to the fringes of its training data, then it hallucinates, or they're trying to stop it doing that, or so it sort of craps out altogether. I agree that it's crossed some uncanny valley, and it's obviously the first thing that's sort of captured the public's imagination. For the first time, I'm going to talk to my non-AI friends. It is possible to have non-AI friends, and they're asking me about, do you know about ChatGPT? And then interestingly, they often have very strong opinions about how it works, which are completely wrong, and often don't ask me, the domain expert, what's going on, which I find curious too. So people have their own theories. Question?
Well, I mean, I guess, because like Sutskever and Hinton are saying it could lead to superintelligence. And I guess, like, based on the conversation we've just had, we know that we're interpolating a data manifold, and we know that these, from a computational point of view, it's got fixed compute, fixed width, and so on. So, how could it possibly be a superintelligence?
I don't think that it could. I mean, it would have to start somehow manipulating its internal representations to make them more coherent, to come up with new ideas and then test those and embed them in its body of knowledge. It really has no way to learn anything new other than its context vector, which it forgets every session. So even if it did have a way to manipulate the information that it had introduced into that context vector and formulate it into something new, perhaps perform some logical deductions on it or come up with some new hypothesis based on it, it has no way to even remember that. So we're missing all kinds of parts of the puzzle. I don't see how you could look at that and think, superintelligence is around the corner.
Yes.
I mean, question for you. I don't like talking about superintelligence because I think it's just a untalkable about topic. But we could talk about AGI. So how far is it to AGI?
Well, I mean, I guess like part of the reason I find it strange is, I think these folks think that there is such a thing as a pure intelligence, and if it has just learned a data manifold, then that must be situated because that's the data we've produced in our physical environment here on the planet. So, all of this has been reduced into a data representation, and we're interpolating that. As you said, it's non-interactive, so it can't, seek new information, and it's non-reflexive, so it can't reflect on its own context or anything like that. So it's just an information retrieval system which has become part of our cognitive process.
Yeah, I don't even like the word intelligence. I think capability is a better word to use. It has certain capabilities. Some of those capabilities are better than humans. It can tell you right now the recent history of epigenetics off the top of its head, and I cannot do that. I think we would be much better to stop using the word intelligence, to start talking about capabilities, because that's a very concrete thing. You can say it can do this task or it can't do this task. And what does AGI mean? It means that for some broad set of capabilities, it can do a large enough proportion of them that we think this is general intelligence.
Even that,
and that's measurable.
I'm not a huge fan of that, and I guess I'll explain why. So yeah, I mean, intelligence. I love this this Chinese proverb of Mount Lu, which Pei Wang talks about. He's an intelligence researcher, and he basically says it's a complex phenomenon that is beyond our cognitive horizon. And just like this mountain range, Mount Lu, depending on your perspective of the phenomenon, the range looks completely different. So you do get these different perspectives, like capability, behavior, structure, principle, and so on.
Well, so I guess I told you my perspective.
But the reason I don't like because capability is like, a behavioral interpretation of intelligence. And the reason I don't like that is GPT doesn't do anything, because all cognitive processes are kind of externalized and physical and so on. And, we enact a cognitive process when we use it. So the artifact itself, in some sense, doesn't have any measurable capability.
I think I disagree with the premise that GPT doesn't do anything.
Well, but it doesn't. I mean, it's just a bunch of... I guess this is quite an esoteric, externalized argument of cognition, because you could argue that a chess computer, like the meaning of the computation is in its use, so it doesn't intrinsically do anything. We use it as part of our cognitive physical processes.
Give an example of something that does do something. This is... I think you're using this word this phrase in a very specific way that I don't quite follow.
Well, we do stuff. We scuba dive. We actually do stuff. And maybe I'm just being a human chauvinist, but I'm completely on board with it becoming embedded in our cognitive ecosystem. But
also GPT does stuff, not very well, but it does it.
Well, does it though? I don't know. Does it do so? I mean, yeah, like in the way a cat flap does stuff. You can make it do things. It can execute code and so on. But I wouldn't say it has agency. Doesn't do it. I mean, agency is about being able to wrestle with the complexity in your environment as an observer with like limited compute, as Wolfram would say. So it's about that kind of complexity differential between the situation I'm in versus the information I have access to.
And I feel you're going to push back on this, but how do you see reinforcement learning then? Isn't that exactly what you're talking about? There's literally something called an agent that has agency, maybe via only a sort of dumb algorithm that does something random until it hits on some reward, but it explores its complex environment, it solves problems, sometimes because it's getting direct rewards, sometimes because of priors we've put into it, like essentially curiosity. You don't see that as doing something?
I don't know. I don't see that as dramatically different from the cat flap scenario. I guess it's... I love this Fristonian idea that agency is actually a description of certain dynamics, which is that you get this kind of like locus of information density where a thing is effectively planning many steps ahead. So you could say, therefore, it has agency. So in the case of reinforcement learning, the thing I don't like about that is, again, we can talk about free will, but someone has designed a reward function. The final chapter of your book is all about ethics and algorithmic fairness. And right now, there's this interesting juxtaposition between near-term safety and long-term safety. In fact, I'm concerned that the word safety has been conflated in its meaning, and people are using one word for long-term and near-term risks. And in your book, I think you were mostly focused on the near-term risks, like, the bias, the misinformation, the fairness, and stuff like that. But yeah, tell us about the chapter.
Right. So yeah. Let me tackle the chapter first, and because the chapter was co-written, by which I mean he did all the work, with a researcher called Travis Lacroix, who's at Dalhousie University, which is in the east of Canada. I didn't feel personally, I'm an engineer, I didn't feel personally confident that I could write a intellectually coherent chapter on ethics, but I was strongly encouraged to. I mean, it's sort of interesting that in an engineering textbook now we need a chapter on ethics, and that's because of the sort of force magnification of this technology. It's very powerful. You can read this book and go and build things that are not good for society, and so it's imperative that you at least think about ethics. I'm not trying to tell you what to do. So I wrote this chapter with Travis, who, by the way, has his own book coming out next year on value alignment, which people should check out. And he comes from a philosophy background, so we went through a whole bunch of iterations of him using long philosophical words and me trying to chop that down until it could be easily understood by engineers. And we cover some aspects of this that are commonly discussed in our world, as you say, bias, explainability, things like that. Some more philosophical things about moral agency and value alignment, which are more discussed probably in his field. I think I only let him use the word epistemology once as a compromise. But I think the interesting thing about that chapter is more the kind of conclusion of it, which is, it's an appeal to scientists to realize that you have to be aware and take responsibility for the actions you take, and that you think you're just doing maths and this is value-free, but everything you do is, they would say, value-laden. So, and that's often deeply, deeply baked into what we do, so much so that you can't even see that. So the very fact that we judge our papers based on only state-of-the-art, whether you've got state-of-the-art, and we don't report whether they're fair, whether they're explainable, how much carbon needs to be emitted to train them or to run them. That is a value that is baked into our community that we don't necessarily think about. And so the book ends with an appeal to sort of interrogate yourself and think about the impacts of your work, which communities it's going to affect. Individual scientists don't necessarily have a huge amount of control, but you have some control. You can choose who you work for. You can choose which problems you choose to work upon. In some sense, it's a collective action problem in that individual people don't have very much control, but collectively you can do things if you organize and decide that this is the kind of things we should be pursuing or not pursuing. And so that's the way the book concludes. And then, I'd
Can you hear me now? Can you hear me now? Can you hear me now? Okay, good. Okay, so let me just, the new studio template spun up and it's supposed to be able to run 24/7 as long as it uses the free CPU tier. Now, yeah, it just opens up new. Okay, that's fine. I'll publish it at the moment. That's fine. I can share it with someone if I want. Okay, this is what you do. So imagine if you wanted to like start where I was yesterday. There was like packet pay test was in progress but not finished. Stage line tic-tac-toe was working, and so was the task, the app. Where's the task app? Oh yeah, this is the task app. Invent Store is actually the task app. So you can go open integrate terminal, and you can run tic-tac-toe, or you can run this one if you want. Port equals 33, whatever. npm run dev or npm run start, one or the other. Wait for when you get more. Oh, script first of all. Oh, you know what you have to do first? I think I have to npmi first. Yeah. Cancel that. npm install. I don't think so. Something's wrong. The CPU's pegged? Yeah. It's because it's loading the data like crazy. It's just the machine still restoring data. I'll give it a minute. Interesting. Sorry, it took that long just to do NPI and get back to it. Normally it doesn't take that long if the studio is already hydrated. And I got distracted anyways. Because I'm exhausted and I should sleep. I did not sleep last night again. Except for maybe a minute. A few minutes here and there maybe. Drifted off. I don't know how it doesn't fry my brain. I don't know. I kind of learned how to do some mindfulness meditation years ago because I was insomniac and it helped. I need to get tired and just meditate it. It's very relaxing. I take a bath and I just lay there in the tub sometimes and I might not fall asleep, but I'm very relaxed and meditating basically. Rest. Some people said that sleep is not necessarily required, but rest definitely is. You can go insane without sleep, but that's because of the lack of rest. Look at that, it's starting to work. Right. Good day. Good day. I don't hear anything. Oh, now I do. Good. How's it going? There's a yeah. I had to I had to shut down Twitter and then restart Twitter on my phone to be able to connect. Yeah. Yeah. I tried clicking it like the button and getting in a bunch of times. I just couldn't get into the room. So if anybody's having problems, you might want to restart your Twitter client. Maybe there's a new version. Just this space, I think. Yeah. Okay. I'll go there, navigate to there. I'm going to end my stream for now because I'm still streaming. So I'm going to end mine. Where's stop streaming? I'm joining the sCrypt Hackathon session. So go to the sCrypt platform's pin tweet